Hello. It's a pleasure to be able to present some of our recent work in this virtual conference. So I'm going to talk today about virtual modeling of soft tissue dynamics. So in medical examination, there are different modes of information gain, such as haptic, visual, or auditory sources of information, which practitioners usually use to determine locations of abnormalities and make diagnosis. And most of the time, this sort of training and knowledge is tacit for them. So it really takes a lot of time and experience to gain this knowledge and connect all of these inputs together in order to be able to detect any abnormalities and make diagnosis. So in order to reduce this time, in order to help them to go quickly into their learning and training, there is this idea of a robotic patient that can provide both visual feedback, like with facial expression, can provide auditory feedback, for instance. And of course, it's very important that the robotic patient can have correct tissue deformation under the forces that are applied to them. So currently there are robotic phantoms. I have shown an example here that is from Trish's lab and published in 2017. Such phantoms are actually quite useful because they can be used in a physical environment to understand how is the interaction between a hard inclusion, like here is a hard nodule, with the soft tissue around it, and when finger is pressing that, then and moves in different directions, how the location of this nodule, the properties of the tissue are affecting the amount of haptic force, haptic feedback that is received by the finger. But of course there are questions about the fidelity of such physical surrogates. So I would say the first thing that we need to check is the mechanical properties of the tissue replacement. Of course, this situation is dynamic, so we need to look at rate-dependent dynamic properties of the tissue, as well as non-linear properties, because we have large deformation. Of course, the other thing is the anatomy. So here is an extraction of a hypothetical patient, I would say, but in reality we have the whole patient under the palpation. And of course, interaction between different tissues is another thing that needs to be checked in order to improve the fidelity. So probably the best example of a most advanced type of surrogate, physical surrogate models, can be found in the automotive industry, of course, where there is much more money. So this is the Hybrid 3 dummy. It was born in 1976, was designed in the GM. You can see a cross-section of different parts of the dummy. It has a combination of hard and soft materials, and these are supposed to represent different tissues. They are not necessarily anatomically correct, but they provide the response that they are designed for. For instance, the response of the neck in whiplash is very important, and this dummy can really well represent that in a crash, a rear crash. I think it was designed for a frontal crash. There is another dummy for rear crash. So you can see, even in designing these physical surrogates, it has not been possible to have one dummy that can represent both rear and frontal crash, and we have another dummy for the side crash. So there are limitations even with these most advanced surrogate models. And perhaps one key limitation you can imagine and you can see in this figure is that it has no brain. And this is where it's my personal interest in my research. So I'm going to use this as an example to move into virtual modeling of soft tissue dynamics. So one approach to virtual modeling is using the finite element modeling approach. It's a computational approach. I'm using the brain example to explain a bit more how it works. So these models are based on anatomical details. So these anatomical details can be found by using MRI scans, CT scans, for instance. In this case, we have an MRI scan of a healthy subject, and we have more advanced scan. So what we have done, we have segmented these scans to have a good definition of the anatomy of different tissues like skin, skull, the fluid around the brain itself. And then we represented every voxel of these volumetric images with these cubes So you can see here square, but in 3D you can imagine it's a cube. So these cubes are called finite elements, and basically they define the geometry of different tissues with quite high fidelity. You can see the groups, the wrinkles on the surface of the brain, as well as different tissues. So once we have this geometrical definition of the anatomy, we define the relationship between force and displacement. And these are done by using constitutive models. So in this situation where we have soft tissues, we are dealing with materials that are rate dependent, they are viscoelastic materials, they are nonlinear, so they are really different to most of the engineering materials that we have seen, like metals, like wood, etc. So these materials are soft, so they have nonlinear rate dependent properties, and we define this by using in this case visco-hyperelastic material models. At the end, the model that I'm showing here had 1 million of these little cubes that we have defined. So now moving forward, we use these models for different purposes. In this case, we use this model to look at deformation of the brain. In what scenario? One situation is sporting collisions, where we have large forces that go into the brain. And actually neurologists, they have found this type of injury or pathology in the surface of the brain, in the sulci region, these regions. You see accumulation of these abnormal proteins, the tau proteins, at the depths of sulci, and this pathology is called chronic traumatic encephalopathy. It's been seen in athletes who have been repeatedly exposed to head collisions. So we thought, why not to use this computational model to see if the location of forces that we can predict with the model in any way suggests that we can predict the location of the pathology. So the data that we had was from an American football impact that was reconstructed using these dummies in the lab. So from the reconstructions, we had the accelerations of the head, basically the motion of the head in 3 dimensions, rotations and translations. We applied this to the skull, and then we predicted the deformation of the tissue to the resolution of the finite elements. So here is a prediction of our finite element model. It shows the distribution of the deformation, maximum deformation in the short duration, 30 milliseconds of the collision. More technically, this is a first principle Green-Lagrange strain contour that we are showing here. And interestingly, we found that the location of maximum deformations match with the location of the accumulation of these abnormal proteins, which actually is encouraging, shows that the model can provide some insight into the nature of this disease. Now the idea is to take forward what we have learned in the injury biomechanics area and apply it to the palpation. So we gained access to a detailed anatomy of the abdomen from Johns Hopkins University. This is a fantastic phantom that they have created. It has detailed description of the anatomy of different organs, especially we're interested in the abdomen. So we used our image-based meshing algorithm that we use for the brain generation here, and we generated the anatomy of different tissues here. You can see with different colors, with high, with a lot of details. So in one of the applications, we use this for palpation simulation. So you can see here, we have simplified the abdomen, so using a single tissue here, which has nonlinear rate-dependent properties. This work was done by Florence. She has also modeled the finger, it has the nail, and she's now modeling a palpation. You can see the finger pushes down and moves across the tissue. So here is a side view, and interestingly what she has done, she has included a hard nodule here. This has a stiffness that is 3 times higher than the surrounding tissue. So what she has been looking for with this model, so you can see another simulation. So the finger goes down, we can then measure the force that the fingertip is feeling here. So when the finger goes down, the force goes up here. When the finger moves across, the force goes up because it's passing by this hard nodule. When the finger stops, we have the relaxation behavior of the tissue, and finger goes back to the left. We see the force drops but remains at constant value here, which is according which is corresponding to the initial indentation, and then it continues. So you see that such simulation can provide very valuable information for us with a virtual model. It can provide the force at the fingertip. It can provide the stress distribution across the abdomen. We can then use such a model to test a large number of scenarios related to various abnormalities. So we can simulate different abnormalities and see how the depth, the direction, the frequency of the finger motion can enhance the information gain. And this is absolutely important for us because we want to move forward and want to understand the nature of palpation. So this mechanical insight into the palpation problem is absolutely important. But of course we have limitations here. As you saw, we didn't have all the tissues here modeled in the previous model. We have to include it in the model. The material properties for different tissues should belong to those tissues. So there are data in literature, but still that is a challenging area to find the properties for different tissues and assign it to the model. So basically we again look back into the automotive industry where there is most advances in these areas. And we found a very interesting human body model or series of human body models. It belongs to the Global Human Body Model Consortium. So you can see they have a range of human body models. There is a high fidelity definition of the anatomy of different organs. The tissues are defined with good material properties, which are good for crash testing, and they have been validated for dynamic loading. So we have now got access to this model. Our future direction is to, first of all, use these models and validate their predictions against human data, of course palpation data. And of course if we need to make any adjustments to material properties, we need to consider it in that stage. Once this is done, that model, that high fidelity surrogate model, will help us to design our physical surrogate model. The simulations that we have done so far, they have been quite time consuming. So if you want, for instance, to run these simulations in real time, on the fly, when we are using the physical surrogate, we have to develop lighter computational models. This is why we are looking at surrogate modeling or virtual surrogate modeling to reduce the computational time. And eventually the idea is to integrate this easy to run light computational model with the robot patient physical model, in order to enhance information gain during medical training. Thank you for your attention, and if you have questions, I believe there are different channels to send it to me.